Okay, in the previous example, we were looking at the infinitely large plane with uniform charge distribution. Let's say sigma. And we explored the electric flux through a cube, which was located somewhere here above the plane. Now let's imagine that we place that cube such that part of it is above the plane and part of it is below the plane. Right, this could be an imaginary cube, and the side, all sides are of length L, and we now want the electric flux through the entire cube. So electric flux through the cube is, by definition, the integral of the electric field over the surface of the cube. We need to do that calculation, and we can do it either by brute force or using Gauss's law. So let's do both because they're both straightforward in this case. So if we do the brute force approach, then we have to integrate the electric field over the top part, and the electric field is pointing this way above. My arrows should all be of the same length. We know what the value, what the magnitude of the electric field is. It's in fact E. Well, the electric field is normal to the surface. We calculated this to be sigma over 2 epsilon naught n hat. Right. So the n hat means it's normal, so on the sides the arrows are actually of the same length as anywhere else, and it looks something like that. And so we want to calculate the flux directly from a brute force approach. So we get nothing from the sides, as we've argued before, because the dot product between E and dA is 0 there. So on the sides here we have dA is pointing this way here, this way over here. Up here instead we have alignment of the dAs and the electric field, but that's also true on the bottom. Okay, so let's make a couple here. So everywhere we have a constant electric field that we can straightforwardly integrate. We know its value, right? It's sigma over 2 epsilon naught, and the cosine between the cosine of the angle between dA and E is 1 everywhere. So on the top part, we just get the magnitude of the electric field, which is sigma over 2 epsilon naught, times the area, which is L squared. And on the bottom, we get the exact same thing. So we get the electric field magnitude, sigma over 2 epsilon naught, times L squared. And so the entire calculation reduces to twice that, which is just sigma over epsilon naught L squared. So that's the electric flux through this cube. And now we can do it using Gauss's law, which says that the electric flux through a closed surface is simply the charge inside, Q enclosed, divided by a number, epsilon naught. Okay, so all we have to do is look inside, according to Gauss's law, and see how much charge there is. Well, where is the charge? Well, the charge is right here. So let's make a few plus signs indicating the charge, which is inside of the box or cube. Okay. So if we look at it from above, we see a square, of length L, right? And there's charge density sigma. So how much charge is that? It's just the density times the area. So it's sigma times L squared. We divide that by epsilon naught. So it's even more straightforward. And we can see that whether we do it by brute force or using Gauss's law, we get the same result.